In our ongoing desire to comprehend a vast and mysterious universe, seeing is not just believing, seeing is everything. While we experience life on Earth using all 5 of our senses, in space, virtually everything we know about the universe comes to us through our ability to see. We gather up the light of the stars and galaxies with our telescopes, and by analyzing that light in a multitude of ways, we gradually unlock the secrets of the cosmos. The invention of the telescope changed our understanding of the universe forever, because it allowed the human eye to overcome a natural barrier and see objects that are much fainter and farther away than we would otherwise see. But there's also another barrier that limits what we can perceive when we look out into space, a barrier that can be overcome if we can learn how to see the universe through very different eyes. That second barrier exists because what we experience as light is really a wave of energy. And whether we can see it or not depends on the length of that wave. The human eye can only perceive light waves that range from about 39 to 75 millionths of a centimeter long. That narrow range, known as the visible spectrum, includes all the colors of the rainbow. But where the eye stops, the spectrum of electromagnetic waves, of which light is just one small part, continues. Now, the opening up of that spectrum at many other wavelengths has given astronomers a cosmic rainbow of new possibilities to explore. It began with radio waves. For decades after radio was invented, no one thought it would be possible to receive radio waves from space. Then, in 1931, an American engineer proved that idea wrong. Carl Jansky was working for Bell Telephone Laboratories, trying to identify natural sources of radio interference that might affect transatlantic communications. With a special receiver set up in a New Jersey field, Jansky found a mysterious hiss coming from the sky. Jansky discovered the radio hiss was always strongest when the Milky Way, especially the bright central region of our galaxy, was above the horizon. Something toward the center of our galaxy was producing radio waves. And there were other sources too. An entire radio universe just waiting to be explored. But what kind of universe would the new technology reveal? Looking at the sky through radio eyes, our entire Milky Way shines with the cool glow of hydrogen gas. Even parts of the galaxy that are blocked from our view by thick clouds of interstellar dust can be mapped in this way. Astronomers have used this convenient fact to uncover the spiral structure of the Milky Way. And radio waves can also help reveal more energetic phenomena. A supernova, the explosive death of a massive star, and one of the most spectacular sights in the universe. For centuries after the event, a bubble of energized atoms expands outward, the far-flung remains of the obliterated star. As the supernova bubble crashes into the surrounding interstellar gas, it gives off radio waves, creating what looks like a bright wreath of radio energy. A black hole is formed when matter is squeezed to infinite density, creating a bottomless pit in space. Once inside, not even light can escape the black hole's irresistible pull. On the way in, gas and debris swirl ever closer to the edge of the black hole. Some of this gas manages to narrowly escape and instead feeds massive high-speed jets of electrically charged particles, which fire outward along the black hole's axis of rotation and become strong emitters of radio energy. Today, astronomers know the radio waves emanating from the center of our galaxy, the same signal Carl Jansky first discovered, come from a giant black hole as large as a solar system. And the Milky Way is not alone. Thanks to radio telescopes, it's now clear that most galaxies contain monster black holes, sometimes with active jets, which are among the strongest sources in the radio sky. Seeing the universe through radio eyes has given us a new perspective, allowing astronomers to discover and study phenomena that were once completely unknown. But radio is just the beginning. There are many other ways to see the universe, especially when we leave Earth behind and begin to observe with new eyes in space. The universe that is most familiar to the eye is the universe revealed by light. As stars and galaxies shine across the vast reaches of space, their subtle colors carry important clues about temperature, chemical composition, and distance. But all the colors of light we can see are just small parts of a much larger spectrum that stretches out well beyond the range of human vision, from very long to very short wavelengths. At wavelengths shorter than the human eye can see, light transitions into other forms of energy that can only be detected with special sensors. And because it takes a lot of energy to produce them, these shorter wavelengths, like ultraviolet, X-rays, gamma rays, are ideal for studying some of the most energetic and most violent phenomena in nature. The catch is that Earth's atmosphere blocks most high-energy forms of radiation. That's good news for life on Earth's surface, which depends on the atmosphere like a protective blanket. But it also means astronomers need to get their telescopes off the ground if they want to explore the high-energy universe. The Hubble Space Telescope makes an ideal starting point. Its cameras see what our own eyes see. But by using special filters, astronomers can also zero in on the hotter, ultraviolet part of the spectrum. By showing only the very hottest stars, Hubble gives astronomers a chance to peer deep into a galaxy's core. Another telescope, the Galaxy Evolution Explorer, or GALEX, is dedicated to looking for sources that shine bright in ultraviolet light. These are the most energetic and short-lived stars we know, and astronomers believe they may hold clues to how the galaxies formed and evolved. That's because the hottest stars we see today may resemble the very first stars that formed when the universe was just a small fraction of its current age. When those stars died, their cores collapsed to form black holes. And some theories suggest the black holes merged to form even larger black holes like those we see at the centers of galaxies today. GALEX has also found other ways to bring hidden details about the stars to light. For example, the aging and bloated star known as Mira is too red and too cool to be observed in the ultraviolet. But GALEX has found that Mira is generating a wind of high-speed particles, which smash into the surrounding interstellar gas, creating a glowing tail that reveals the star's movements for the past 30,000 years. Leaving the ultraviolet behind, the Chandra X-ray Observatory is our guide to an even higher temperature X-ray universe. To collect X-rays, Chandra uses a series of 4 nested cylinders coated with iridium to reflect and direct the X-rays into a sensitive detector. Only objects with temperatures of millions of degrees are able to produce X-rays through heat. Here, a supernova that was witnessed by the astronomer Tycho in 1572 appears like a frozen fireworks display when seen in X-rays. One of the most spectacular sights in the X-ray universe is this stunning panorama from Chandra, showing the region near the center of our Milky Way galaxy. This area is hidden from optical telescopes by dense clouds of interstellar dust. But X-rays, which pass right through the dust, unveil a chaotic spacescape full of churning hot gas and bright specks that could signify where neutron stars and black holes are devouring companion stars. At the very heart of this fascinating region is a bright cloud of gas surrounding what is thought to be the location of the Milky Way's giant central black hole. When combined with a view in infrared light, Chandra's X-ray image is our most revealing glimpse yet of the most extreme location in our galaxy. Looking beyond X-rays, astronomers have also begun to explore the universe at even shorter wavelengths and higher energies. NASA's orbiting Fermi telescope is designed to detect gamma rays. Fermi registers their arrival as they rip through canisters filled with metal plates and split into pairs of matter and antimatter particles. This design allows Fermi to deduce the energy and incoming direction of the gamma rays. One of its most surprising results has been the discovery of 2 giant bubbles of energetic particles emanating outward from the center of our galaxy. The cause of these bubbles, each 25,000 light-years tall, remains unknown. They could be linked to outbursts from the Milky Way's giant black hole. Even more perplexing has been the mystery of gamma-ray bursts, vast explosions that appear all over the sky at great distances, far from our own galaxy. Astronomers believe they may mark the births of black holes from the collapse of massive stars. Perhaps only the Big Bang itself can top an event as powerful as a black hole's birth. But to look for evidence of the Big Bang, astronomers must change perspective yet again and see the universe in a different light. The more we can expand our vision beyond what the eye can see, the more we can learn about the universe. Even in the narrow range of light that the human eye responds to, small differences in color can yield great storehouses of information. Here, with this magnificent view of the Whirlpool galaxy, over 30 million light-years from Earth, the Hubble Space Telescope plays witness to a great cosmic cycle. The giant spiral waves sweeping through the disk of the galaxy show where vast clouds of hydrogen gas, triggered by gravity, are collapsing to form new stars. The stars light up the gas, which gives off a pink light. In comparison, stars are not forming near the galaxy's central region. There, a population of middle-aged stars gives off a cooler, yellower light. But now, as seen through an infrared camera on the Hubble, we find the galaxy is threaded through with glowing wisps of interstellar dust. The particles that make up the dust are tiny, like smoke. But collectively, and through infrared eyes, they reveal what is going on below the threshold of human vision. Infrared telescopes offer astronomers a way to probe the cool universe at wavelengths longer than the human eye can see. Since the atmosphere blocks most wavelengths of infrared, the telescopes that are best able to exploit this part of the spectrum are in space. The Spitzer Space Telescope is sensitive to the infrared light that is nearest to visible light. With the Spitzer, many celestial objects look familiar, but also just a bit different. Here, the North American Nebula gets its name from bright and dark clouds of gas and dust that vaguely resemble the familiar outline of the continent, complete with the Gulf of Mexico. But using Spitzer's infrared vision, the dark regions suddenly light up, revealing the structure of the dust clouds. Pushing farther into the infrared universe is the Herschel Space Observatory, currently the world's largest orbiting telescope. Herschel looks at longer wavelengths than Spitzer, so it sees even cooler objects. Its specialty is peering into dark, dust-shrouded clouds to see the embryos of newly formed stars. Herschel has shown that even within the coolest, darkest clouds of our galaxy, matter is in motion, like a vast cloud of billowing smoke. Herschel has also cast its gaze beyond the Milky Way to our nearest galactic neighbor, the Andromeda Galaxy. In this view, we see Andromeda first through visible light, with its bright stars and dark lanes of dust. But with Herschel, the stars fade to black, and the dark dust shines like brilliant ribbons. Infrared telescopes are beginning to probe the most distant corners of the expanding universe, where light from rapidly receding galaxies is shifted to longer and longer wavelengths. In the future, infrared telescopes will be crucial as astronomers continue to peer farther and deeper in search of the very first galaxies and the first stars. But even farther down the spectrum, where infrared light transitions into radio waves, astronomers have found a signal that announces the beginning of the universe itself. That signal, which comes to us from every direction in space, first showed up by accident in a horn-shaped antenna operated by Bell Labs in New Jersey. Two researchers, Arno Penzias and Robert Wilson, made the discovery in the mid-1960s, not far from where decades earlier, Carl Jansky first detected radio waves from the Milky Way. Without realizing it, Penzias and Wilson had discovered the cosmic background, light that was emitted by our universe when it was filled with white-hot gas in the aftermath of the Big Bang, nearly 14 billion years ago. Today, satellites are probing the cosmic background and mapping its features in detail. These small variations in wavelength and temperature can reveal volumes of information about the physical properties of the early universe, and may eventually help us understand what caused the Big Bang. "400 years ago, astronomers first turned the telescope to the heavens and discovered there was more to the sky than meets the eye. Now, a host of new eyes in space, as well as radio ears on the ground, have opened up the entire spectrum, giving us a cosmic rainbow of perspectives as we try to piece together how the universe works." It's not just what we see that has changed over the course of this incredible journey, but the idea of seeing itself. Of all the places on Earth where humans can feel close to the heavens, none can beat the rocky desolation of Chile's Atacama Desert. Here, where rarely a cloud is seen, peak after towering mountain peak thrusts into the dry, still air. And each night, as darkness descends, the stars shine with an unblinking clarity that rivals the view from space itself. Once nothing more than a distant curiosity, this harsh and remote landscape has become the focal point for some of the most exciting developments in our exploration of the universe. And there is much more to come. Today's state-of-the-art telescopes are larger and more expensive than ever. So to get the most out of them, astronomers want to put those telescopes where they can be used to their best advantage. The Atacama offers just such a place. It's the driest desert on Earth with only a handful of cloudy nights each year. The airflow is remarkably steady, and it's far from cities and towns that throw light into the night sky. Put it all together, and you have a gateway to cosmic discovery. Today, Chile is home to some of the world's most impressive observatories. And here, high atop Cerro Paranal, is the most impressive of all. This is the VLT, short for Very Large Telescope. Despite its name, it's actually 4 large telescopes plus 4 smaller ones, which can either work independently or together, like a giant light-collecting machine. Part of the secret to the VLT's success is its location. Perched more than 2.6 kilometers above sea level, Cerro Paranal boasts the ideal atmospheric conditions for astronomy. But there is more than an exceptional sky at work here. To produce views that challenge the Hubble Space Telescope for beauty and clarity, the VLT also relies on some exceptional technology. It starts with each of the 4 large telescopes' main mirrors. Each one is a single piece of aluminum-coated glass 8.2 meters across, but less than 20 centimeters thick. Such a large but thin mirror would naturally bend under its own weight. To prevent that from happening, the VLT employs a strategy for keeping its 4 giant mirrors in shape. Each rests on a bed of 150 pistons, called actuators, which can press on the mirror at different points. The actuators bend the mirror by just the right amount to maintain its ability to focus, no matter how the telescope is moved or tilted. Such precision is perfect for roaming the rich star fields of the southern Milky Way. Here, like a bubble frozen in time, the VLT spies the Dumbbell Nebula, a ballooning cloud of gas made up of the outer layers of a dying star. Nearly 20 times farther away, the VLT finds a burst of celestial fireworks in mid-eruption. The largest and brightest stars in this cluster would outshine our Sun 8 million times over. These images are all the more breathtaking because they are taken from Earth, not from space, by an observatory that is swimming in air. Even on the clearest of nights, unseen turbulence in the air pushes starlight around as it journeys through Earth's atmosphere. The same effect is what makes the stars twinkle. To get around this problem at VLT, all the light gathered from each telescope's main mirror is bounced onto a second mirror, which can rapidly deform to reverse the distortions caused by the moving air. Like other observatories in Chile, the VLT is in a perfect position to put its cutting-edge technology to use. In the northern hemisphere, the central regions of our Milky Way galaxy can barely be seen above the horizon. But in the south, the galactic center arches high overhead. Shrouded behind dark ribbons of interstellar dust, the center of the Milky Way is an elusive target. But the telescopes of the VLT can also detect infrared light, which can pass through the dust. In this unprecedented image, the VLT has revealed the spectacular concentration of stars at the heart of our galaxy. Here, dozens of giant stars crowd a region that is only 2 light years across. Astronomers can now return to this view again and again to see the stars moving as they orbit the giant but unseen black hole lurking at the heart of the Milky Way. In every journey, there is always another mountain, another spectacular view. What we will find, we do not know. What we do know is that in the journey to explore the cosmos, our path leads through the Atacama. By night, the skies over Chile's Atacama Desert offer a dazzling spectacle. Some of the best views of our universe found anywhere in the world. By day, the stars fade away, and the giant telescopes on their mountain perches retreat into their domes, shunning the harsh southern sun. Yet, even in broad daylight, there is still plenty of universe to explore. Radio waves reaching the Earth from the depths of space carry information about distant events in our galaxy and far beyond. For years, radio astronomers have been scanning the skies with giant dishes and picking up the faint signals that come from sources all over the universe. But there's one frontier left to conquer. Astronomers call it the submillimeter. That just means radio waves that are very short, less than 1 millimeter across. It turns out some of the most interesting phenomena in the universe, from the births of stars to the most distant galaxies, are giving off energy at those wavelengths. But there's a problem. Water vapor in Earth's atmosphere is very good at blocking submillimeter waves. So, to see the universe at those wavelengths, astronomers need to go to one of the highest and driest places on Earth. And that place is here, 5 kilometers above sea level. Nestled among the high peaks of the Andes Mountains, astronomers are building the Atacama Large Millimeter Submillimeter Array, ALMA for short. When completed, it will be the largest and most sophisticated radio observatory on Earth. At its heart, ALMA consists of 66 large dish antennas, some built in Europe, some in North America, and some in Japan, reflecting the international partnership behind the project. Each dish is a nearly perfect parabola, precisely tuned to pick up signals at submillimeter wavelengths. Each dish on its own would be an impressive tool for exploring the heavens. But at ALMA, the dishes will work together as one, creating a giant, steerable receiver that will probe the skies with unprecedented sensitivity, gradually building up a view of the universe as we've never seen it before. One of ALMA's highest priorities will be exploring the complex tangle of interstellar gas and dust that spans the plane of our Milky Way galaxy. In doing so, it will not only witness the formation of stars, but in some cases, it will discern young planets emerging from the debris that surrounds those stars, something that happened in our own solar system 4.5 billion years ago. satisfy the variety of groundbreaking observations that astronomers hope to make with ALMA, the array needs to have more than just a large number of dishes. It must also be able to change the arrangement of its dishes depending on the kind of observation that is being made. For some targets, ALMA will work best if most of its antennas are clustered towards the center of the array. At other times, they will need to be much more spread out to increase the precision of the entire array. At its widest configuration, ALMA's antennas will be spread out over 14 kilometers. Moving these antennas around will not be easy. Each one is a high-precision scientific instrument that also happens to weigh about 100 tons. To do the job, ALMA has two special transporters, as massive and muscular as they are maneuverable. The transporters feature 28 independently controlled wheels and can move fast across the high desert roads. But in practice, when one of ALMA's antennas is being transported, the driver will aim for a gentler ride. The ability to adjust the locations of its antennas is just one way in which ALMA will optimize its view of the heavens and bring a new level of detail to our exploration of the distant universe. Because ALMA will be able to zero in on small and remote objects, it will be perfect for isolating and measuring the properties of very distant galaxies. Looking back to a time when the universe was less than 1/20th of its current age, and the very first galaxies were forming out of the residue of the Big Bang. By taking advantage of some of the most beautiful skies in the world, this incredible new observatory will help transport astronomers deep into the past. What they hope to find will answer some of our deepest questions about the origins of the universe. In one of the driest and most desolate pockets of Chile's Atacama Desert sits a maze of weathered rock formations, sand dunes, dry lake beds, and salt deposits that glint like snow in the desert sun. Here, more than anywhere, the otherworldly quality of Chile's extraordinary landscape seems at its most intense. This place is called Valle de la Luna, the Valley of the Moon. Tourists come to experience what it might feel like to set foot on another planet. In the 1990s, researchers came here to test an early prototype for a rover on Mars. The Atacama seems so much like it's part of another world. Perhaps it's fitting that now it's leading us to new worlds across the galaxy. At the VLT on Cerro Paranal, astronomers have zoomed in on Beta Pictoris, a nearby star easily visible to the naked eye in the southern hemisphere. For years, it's been known that a swirling disk of dusty debris surrounds Beta Pictoris. And more recent observations indicate that at the center of the disk, there's a gap, roughly the same size as the orbit of Saturn in our solar system. Astronomers suspected a large planet was responsible for the gap, because a planet's gravity would sweep that part of the disk clear of the dust and small chunks of debris that had coalesced around the newborn star. But finding such a planet is like looking for a very small needle in a very large haystack. In 2003, by using the VLT's infrared capability, astronomers were able to spot a faintly glowing dot located very near Beta Pictoris. It looked promising, so they waited. 6 years later, their suspicions were confirmed. By 2009, the object had moved to the other side of the star, clearly showing that it is a planet orbiting around Beta Pictoris. The planet is estimated to be 8 times more massive than Jupiter, not a place where we would expect life to emerge. But where one planet exists, there could be more. The Beta Pictoris system, located only 60 light-years from Earth, is just one more reason why astronomers are drawn to the southern hemisphere. By sheer chance, the night sky we see below the equator is particularly rich for stargazers. For those used to the more subdued skies of the north, a first glimpse at the southern Milky Way, with its vast star clouds and dark tendrils of interstellar dust, is simply awe-inspiring. Taking a cue from the scientists at the great observatories, more and more backyard astronomers are now coming to Chile for a chance to glimpse what they cannot see in the north. Here, even a quick scan with binoculars can offer rewarding views of the region's signature constellation, the Southern Cross. Elsewhere, an ordinary digital camera can bring out the subtle colors in the glow of ionized gases where new stars are forming. Like their professional counterparts, the amateur astronomers who come to Chile have found that technology can help them get the most out of the view. For example, the movement of air will cause an image to blur slightly, no matter how good the seeing conditions. But by taking hundreds of images of the same object and then digitally combining them, it's possible to create images of astonishing clarity. Here, the method is used to bring out fine details in the Eta Carina Nebula, one of the great spectacles of the southern sky. Humans have been looking at the stars since before written history and exploring the universe with telescopes for centuries. But it may be that nowhere on Earth have humans found such a strong connection to the night sky as in the Atacama. It truly is a stargazer's paradise. Perhaps it requires being in a place that is far removed from earthly affairs to see the possibilities that lie beyond our own world. With each generation, we have seen farther and encountered wonders greater than we can imagine. From the barren rocks of the Atacama, the path now leads deep into the galaxy. We do not know if our descendants will ever venture to the stars, but should they step away from Earth's embrace, we can, from here, begin to see the way. In the Atacama, we stand poised at the cosmic doorway. What lies beyond is the road to cosmic infinity. In a world of change, the night sky has come to signify all that is eternal. Seasons may pass. Civilizations may rise and fall. But the stars still traverse the heavens each night in a timeless celestial procession. So steady is the light of the stars that the constellations we see each night are the same ones our ancestors gazed upon thousands of years ago. And each individual star could shine for millions or billions of years more. The stars and galaxies convey the impression that the things we see in the universe are permanent and unchanging, at least over the course of a human lifetime. But that's not always the case. One of the most astonishing phenomena in the night sky is so fleeting that most people have never seen it, even though it's very common and can easily be found without a telescope. For generations, the aurora borealis, or northern lights, have enchanted those lucky enough to see them. With their bright colors and strange, wavering movements, the auroras seem to be alive with a supernatural energy, a perception that arises again and again in stories from the past. In North America, for example, the Algonquin people explained them as the light reflected from the campfire of the Creator. While to the Vikings of Scandinavia, they were the Valkyrie, supernatural beings who accompanied fallen warriors on their way to meet the gods. And in many northern cultures, they are simply regarded as the spirits of the ancestors, dancing in the sky. But it was the astronomer Galileo in the 1600s who first named these events aurora, after the Roman goddess of the dawn. Galileo incorrectly speculated that auroras were reflections of the sun's rays. But he did get one thing right. It is the sun that is ultimately responsible for the aurora. It would take 3 more centuries before Christian Birkeland, a Norwegian scientist, hit upon the correct explanation. The aurora, it turns out, are the result of billions of microscopic mid-air collisions. Starting at around 250 kilometers above Earth's surface, electrically charged particles from the sun collide with the oxygen and nitrogen atoms and molecules in our atmosphere. The gases are energized by these collisions, giving off a colorful glow. The different colors relate to the height, energy level, and type of gas. For example, oxygen can glow both red and green, while energized nitrogen can produce a blue or crimson color, or sometimes both at once, which makes the aurora seem purple. The solar particles responsible for all this energizing can be seen most vividly during a solar eclipse. As the moon slips in front of the sun, the blazing light of the sun's surface is temporarily blocked. As the sky goes dark, a feathery glow appears around the silhouette of the moon. This is the solar corona, a region where particles blasted off the sun's surface are heated to extreme temperatures and eventually driven outward into space. As they travel, the solar particles form an invisible current called the solar wind, which blows past the planets of our solar system on its way to the stars. As the solar wind flows past Earth, some of the particles are captured by our planet's magnetic field, which is generated deep inside Earth's core. Like tiny compass needles, they follow the lines of magnetic force heading down to our planet. The magnetic field lines converge near the north and south poles. The aurora they produce are mostly seen far from the equator, closer to the Arctic and Antarctic regions of our planet. Sometimes auroras are dazzling and brilliant, and other times they do not appear at all. The secret to why auroras are sometimes spectacular and sometimes scarce lies again with the sun. The more active the sun, the more potent the solar wind, and the more beautiful the auroras. Like Earth, the sun has its own magnetic field, but the sun's is more powerful and it originates within the hot plasma deep in the interior. The most obvious signs of the sun's magnetism are sunspots, dark patches that appear where lines of magnetic force have broken through the surface. Regions associated with sunspots can be incredibly dynamic, sometimes spawning massive explosions called solar flares, which can release more energy than the detonation of 1 million nuclear bombs. An active sun is also more prone to coronal mass ejections, magnetized bubbles that can grow within the sun's corona and ultimately burst outward, sending billions of tons of energized particles racing through space, turning the steady flow of the solar wind into the equivalent of a hurricane. If such an event happens, within hours, high-speed particles are battering Earth's magnetic field. Down on the ground, the effect is often a spectacular display of aurora. But there are other effects. Violent fluctuations in the Earth's magnetic field can overload power lines and cause blackouts. Because of their potential to disrupt technology on Earth, solar storms are the subject of intense study. That means the aurora have now stepped out of myth and legend to become part of a larger space laboratory, helping us to understand the sun and its influence on our planet. The aurora may be a phenomenon of our atmosphere, but it is directly connected to forces at work far off in outer space. Perhaps it's fitting, then, that we have to go to space to understand it best. Like a delicate sculpture suspended in silent grace, the International Space Station sails over our planet. The station is humanity's most ambitious outpost. It lies only a few hundred kilometers above Earth's surface, yet it is our beachhead into the infinite vastness beyond. With the station, we now have a perpetual eye on our planet from above, a way to see Earth in all its glory, including oceans, continents, and our best views yet of the Earth's colorful aurora. Until the arrival of spaceflight, we really had only one place from which to view the aurora, down on the ground. That's changed now, and so has our understanding of what's really going on when the sky is on fire with northern lights. When it comes to the aurora, it turns out that space is the place to get the big picture.
4, 3, 2, 1, 0.
In 2007, NASA's Themis mission probed the forces that can turn a calm aurora at the poles into an all-sky light show with potentially paralyzing consequences for our technology. 5 microsatellites measured electric and magnetic fields in space, as well as the flow of solar particles during an aurora. At the same time, an array of 20 ground-based stations in Canada and Alaska took wide-angle shots of the aurora while making magnetic measurements. Themis revealed that the energy contained in just one solar storm is equivalent to that released in a powerful earthquake. The mission also found invisible strands of Earth's magnetic field dangling 40,000 kilometers out into space. Called magnetic ropes, these ephemeral fields capture solar wind particles, briefly tying the Sun and Earth together until the ropes unwind and dissipate. A parallel project, Europe's Cluster mission, involves 4 identical satellites orbiting the planet in formation. Their goal is to provide a 3-dimensional picture of how the solar wind interacts with the Earth's magnetic field and produces aurora. Like mapping an electromagnetic landscape, Cluster is helping determine exactly how particles that originate at the Sun gradually find their way down into our atmosphere. These studies from space remind us that auroras are a planet-wide phenomenon, and they should arise wherever the same 3 ingredients occur anywhere in our solar system. Those ingredients include the flow of particles from the solar wind, a planet with a strong magnetic field, and a dense atmosphere for the solar particles to collide with. The planet with the strongest magnetic field in our solar system is Jupiter. A giant ball of gas so large, all of the other planets would fit inside it. Jupiter would seem like a prime spot to search for auroras beyond Earth. Even at a distance 5 times farther from the Sun than Earth, Jupiter's intense magnetic field is strong enough to pull in the solar wind. Io, the closest of Jupiter's large moons, sports its own magnetic field. Gas in its atmosphere glows, causing a small aurora of its own. This field affects particles caught in Jupiter's magnetic web, funneling them toward a specific spot in the giant planet's atmosphere, creating a bright spot in the aurora that changes position with Io. Fainter spots in Jupiter's auroras are believed to be the footprints of Ganymede and Europa, 2 more of Jupiter's large moons. Saturn is another gas giant in the solar system with auroras. First captured in one of the Hubble Space Telescope's early images, these auroras are now monitored by the Cassini spacecraft currently orbiting Saturn. Hubble and Cassini both found auroral ovals around Saturn's poles, but glowing in ultraviolet light. Later, Cassini found a whole new set of auroras glowing in infrared. This aurora, unlike any other before seen, covers the pole rather than crowning it like a glowing ring. The ability to explore the other planets in our solar system has shown us that auroras are not a phenomenon unique to Earth. Anywhere where a moon or planet with a gaseous atmosphere and a strong magnetic field is exposed to the relentless tides of the solar wind, we should expect to see something like the Northern Lights. And now, with technology on our side, it's possible to enjoy these dancing lights as never before. The aurora borealis have inspired our stories and filled our dreams since long before the beginning of recorded history. Yet our efforts to adequately record and study these colorful moving lights in all their ethereal beauty have always fallen short, until now. Today, the advent of digital photography makes it possible to capture the faint and ever-changing light from the auroras. Now, backyard stargazers around the world are putting these tools to use and showing us what until now only a few were lucky enough to witness. An aurora we see from the ground is part of a larger structure in the form of two large ovals centered on the north and south magnetic poles. To see auroras regularly, you have to be under one of these auroral ovals, or at least close enough to catch a glimpse. That means people living in the far north or south have the best chance to see auroras on a regular basis. When there are more particles flowing toward Earth, the ovals expand, covering a larger area and making auroras visible nearer the equator than usual. Observers at latitudes closer to the equator will only see the highest auroras, which appear as a reddish glow in the direction of the poles. In some cases, auroras hang like curtains above the Earth. This is because Earth's magnetic field traps particles from the solar wind and channels them almost straight down. They cannot wander away from the field lines, so from a distance, we see them as sheets of light. Some of the most spectacular auroras of all are those that occur when these shifting curtains of light are directly overhead. They create the effect of radiating lines of moving light, pulsing and emanating from a central point. Such displays are breathtaking, and they ensure that no matter how well we come to understand auroras, we will never cease to be filled with wonder when we see them. When you stop and think about it, no other process in nature so directly connects something that's happening deep beneath our feet in the core of the planet with something that's happening inside a star, our sun. But there's also another way that the aurora may connect us here on Earth to the larger universe that we're a part of. because they are a product of Earth's magnetic field, auroras are a visible sign our planet is largely protected from the bombardment of particle radiation that would otherwise be raining down on us from space. By deflecting and channeling many of these particles toward the north and south poles, the magnetic field acts as a shield, making the Earth's surface safe for life as we know it. Although today we are far from being able to observe other Earths directly, astronomers are now beginning to test the idea that we might someday be able to detect the energy of an auroral display underway on another world beyond our solar system. If such a detection could be made, it would come with some big implications. It would allow us to distinguish between a planet like Earth and similarly sized planets like Venus, which has no magnetic field and is completely inhospitable. In fact, the presence of auroras on another planet would be our cue to look for signs of life. Mysterious and beautiful, intriguingly complex, we have now come to realize that the auroras that light up our night sky are also a colorful calling card that advertises our existence. Perhaps the auroras of another world will one day help lead us to our first meaningful contact with other conscious beings in the universe, and point the way to a cosmos full of light and life. The universe engages us with both its unending vastness and its rich diversity. The farther we look, the more we discover, and the more we realize how much there is yet to understand about the cosmos that surrounds us. The challenge for astronomers is that our view only extends so far. Our technology allows us access to a finite part of an infinite reality. Physically, we are bound to the Earth and the nearby worlds of our solar system. With our observatories, we can only see the light that happens to come our way from the stars and galaxies. How then can we hope to explore the parts of the universe we can't reach and can't see? Fortunately, there is a way. One that doesn't just enhance our senses, but enhances our ability to imagine the universe in a virtual way.
Once, there was only one way to explore the distant universe, through the eyepiece of a telescope. But times have changed. Astronomers can now turn to their supercomputers to conjure up representations and simulations of what goes on in reality in order to see and understand reality better. Along the way, they've created something that's close to a new kind of art, the art of cosmic visualization.
As a starting point, computers can help transport us to where we can have a new and better vantage point on places we've already explored. One such place is the Moon.
Humans have not set foot on its desolate surface since 1972. Since then, many robotic spacecraft have orbited our satellite, taking countless images and sending back a torrent of topographic and mineral data. Most recently, scientists have obtained some of their best views of the Moon with NASA's Lunar Reconnaissance Orbiter, LRO for short. LRO carries a powerful camera as well as an altimeter, which bounces laser light off the Moon's surface and measures the time it takes to reflect back to the spacecraft. Together, this information can be assembled in a computer to provide a three-dimensional perspective of lunar craters and mountains, bringing us much closer to the surface than the spacecraft actually traveled. What is most astonishing about this particular flyover is that, although it looks very realistic, no astronaut has ever seen this part of the Moon. And scientists are interested in finding out more. These views are not simply aesthetic choices. They are created to help planetary scientists better understand the complex history of the Moon's ancient surface and identify future landing sites where rovers or astronauts may one day unearth a deeper understanding of our nearest neighbor in space. After the Moon, humanity's next step into the great beyond could well be Mars. No planet apart from our own has been the subject of such intense scrutiny and the destination of so many robotic missions. In recent years, it seems an entire fleet of spacecraft has descended on Mars, either roving over its terrain or imaging its surface from orbit. Like its lunar counterpart, the Mars Reconnaissance Orbiter studies the planet from high above. But this computer-simulated flyover, created with data from the spacecraft, makes it feel like we're staring out of the window of a Martian airplane. Traveling to Mars would present the biggest challenge humans have yet faced in space, and it is still far from routine for the robots blazing a trail here. Lots of data is key to planning an effective exploration. Even for an unmanned rover, it is crucial for researchers to know what is waiting for their vehicle before it sets down on the planet's surface. Here, information from Mars Reconnaissance Orbiter has been turned into an in-depth tour of Gale Crater, now selected as the landing site for Curiosity, the next rover to be sent to Mars. The crater reveals an intriguing landscape. Sections of its floor are covered with ancient sediments that may have been deposited long ago by flowing water. At the center of the crater is a towering mountain, 5 kilometers high. How it came to be there is unknown, but its layers of rock were laid down at a time when Mars may have been warm and wet enough to support life. Researchers hope views like this will help them chart an optimal surface route for Curiosity's challenging mission. In a completely different way, astronomers have used computers to obtain a three-dimensional view of the Orion Nebula, one of the nearest and most spectacular star-forming regions in our galaxy.
Here, the computer allows us to travel many times faster than the speed of light, flying around the cluster of bright stars at the heart of the nebula. These stars illuminate the hydrogen and other gases within the nebula, making them glow. They also drive back the gas with a strong stellar wind, which creates a hollow space inside the nebula and exposes the embryos of new solar systems in the midst of formation. Such views are both artistic and scientifically accurate, but they merely scratch the surface. The real power of computers involves not just exploring new landscapes, but in revealing the hidden forces at work in shaping our universe. The roots of astronomy lie in our attempts to keep time. Patient sky watchers once used the stars to divide the night. They tracked the sun's yearly trip through the stars by watching the constellations appearing out of the sunset and fading into the dawn. Now, the arrival of powerful computers is allowing astronomers to deal with time in a new way.
The real power of supercomputers in astronomy is not simply to show us what the universe might look like in places that are too hard for us to get to. It's to show us how things change over vast timescales that we could barely comprehend, let alone experience. In that way, a computer can be like a cosmic clock. Just set it running and see what kind of solar system or galaxy or universe takes shape.
Astronomers have long thought our solar system formed out of a disk of debris that swirled around the newborn sun 4.5 billion years ago. When we peer with telescopes at star-forming regions elsewhere in our galaxy, we can find evidence of disks around other young stars. But how exactly did it happen here? And how did it lead to the family of planets we recognize as our solar system, including one planet, Earth, that ended up in just the right place to support life? Because we can't go back in time to see how we got here, astronomers use the information gleaned from observing other stars to set up computer simulations of our solar system's formation. Such simulations offer a virtual laboratory to test detailed theories of what really happened. Astronomers have had some success modeling solar systems, but can we turn the clock back even farther to simulate the birth of galaxies? According to current theories, the galaxies we see today formed from smaller galaxies, created when the first stars died and left behind black holes that act like cosmic glue. The black holes came together, creating cores around which larger galaxies formed. As we see, galaxies did not form in isolation. Often, many formed in the same part of space, gathered in clusters and superclusters. In some cases, two galaxies may run into each other. This can be a gentle collision, a cosmic fender bender in which the vast distances between the stars in each galaxy means they pass right through each other, distorting only slightly due to their mutual attraction. In other instances, simulations show how celestial fireworks can occur, with galaxies smashing into each other, exploding, and recreating in a completely new form. As we look around the sky, we see many examples of interacting galaxies. And now, supercomputers are helping us turn time backwards to see how they got that way. Even our nearest galactic neighbors are in the process of interacting. The Andromeda Galaxy is 2.3 million light-years away. Through a telescope, it's also possible to see a smaller companion galaxy. Modeled here, with each star represented as a point, we see the two galaxies engage in a long, slow, gravitational waltz. According to this simulation, the dance leaves a big impression on both galaxies. But, as is usually the case, it is the smaller partner that is more obviously affected by the gravity of its larger neighbor. Our own Milky Way is smaller than Andromeda, and observations reveal that we are also on a collision course with this galactic monster. Flashing forward billions of years into the future, we see the fate of our own galaxy is to collide and ultimately to merge with Andromeda. Will this affect our planet? It's hard to imagine that it will not. By then, Earth will be into its old age and very likely no longer a habitable world for humans, or anything like us. But here, with the help of a computer, we can see how the future will play out far beyond the boundaries of our own experience. After centuries of scanning the skies with telescopes and decades of sending unmanned probes to other planets, we should know our own solar system pretty well. But we can't see everything. For example, we know the formation of our solar system should have spawned a zone of small icy bodies well beyond the orbit of Neptune. Pluto, discovered in 1929, may simply be one of the largest members of this group, collectively known as the Kuiper Belt. Since 1992, many dozens of Kuiper Belt objects have been discovered, and estimates suggest there could be up to 70,000 more. Now, a computer simulation can help show us how the Kuiper Belt may appear to an infrared telescope observing our solar system from a distance. It appears as a glowing ring because collisions within the belt create dust which radiates a faint infrared light. A gap in the ring reveals the presence of a planet. In this case, Neptune. Scientists can also take the simulation backward in time to see how the Kuiper Belt is likely to have changed over billions of years. Eventually, it devolves back to a simple ring, exactly what's been found surrounding some other stars that are much younger than our Sun. The computer is our gateway to understanding the hidden influences at work in the cosmos. The ultimate hidden influence is the influence of dark matter. Discovered through its gravitational pull on stars and galaxies, dark matter gives off no light and is not directly observable by any other means. A lump of dark matter would pass through Earth like a ghost, since it does not interact with ordinary matter at all. Yet the dark matter in our universe outweighs normal matter by 5 to 6 times, and its gravitational pull has had a profound effect on the way the universe has evolved. Using computer simulations, we can now imagine what it would be like to fly through our own galaxy and experience it as though we were wearing dark matter glasses. The effect is something like driving through a snowstorm, but on a galactic scale. In this visualization, everything made of atoms, including stars and planets, have been rendered invisible. What we see is only dark matter, which the computer shows us forms in countless clumps that orbit around the galaxy's center. Over the course of our solar system's history, Earth may have flown through many of these clumps, but we would never know this. However, the presence of this dark matter guides how the stars move and shapes our galaxy. The effects of dark matter grow even more significant as we look to larger scales. For example, when we peer out to the universe over hundreds of millions of light years, we find the galaxies are not distributed randomly. Instead, we find there is a pattern to the way the galaxies are organized. Astronomers call it the cosmic web. Matter has tended to concentrate, and galaxies have tended to form in sheets and filaments, leaving surrounding voids or bubbles where matter is relatively scarce. What is the source of this cosmic web? With the help of supercomputers, astronomers have been able to determine the answer. When dark matter is added to the equations that show how the early universe took shape under the influence of gravity, it is the cosmic web that emerges. There's no question that the use of supercomputers has both broadened and deepened our knowledge of how the universe works, and that computer simulations have allowed us to travel through time and space in a virtual way so that our minds can go where our bodies cannot follow. The best part is this is just the beginning. Supercomputers are only getting faster and better, and that means the virtual universe that's opening up before our eyes is probably going to be even more imaginative and spectacular. Perhaps there's an even deeper insight we can glean from the new power of computers and the way they are being used to help us understand nature at the largest scale. What these simulations tell us is that the cosmos is inherently mathematical in nature. Whatever our universe is, and however it came to exist, it is governed by numbers and relationships that can be represented in a computer. The universe is not getting smaller or easier to understand, but with computers to aid us in our future explorations, we know that much, much more of it will now be within our grasp. For those who would journey across the vast reaches of interplanetary space, the solar system offers many breathtaking sights. But nothing quite compares to this. A giant world made of gas, completely encircled by a perfect gleaming set of rings. Like a cosmic illusion conjured out of the infinite expanse of space, Saturn delights the eye and challenges the imagination. Yet Saturn is no illusion. It is an exotic natural laboratory that can help shed light on how planets form and perhaps on how life evolved.
4, 3, engine start. 1, 0, liftoff.
In July 2004, after traveling in space for nearly 7 years, NASA's Cassini mission arrived at Saturn, marking the start of a bold new chapter in solar system exploration. Cassini is not the first spacecraft to reach Saturn, but it is the first to remain in orbit around the planet. It is also the most expensive and ambitious planetary probe in history, gathering data and images over a long period that have completely revolutionized our understanding of Saturn and its many unique features. From its swirling, dynamic atmosphere, to its dozens of exotic and mysterious moons, to the trillions of floating bits of ice and dust that together make up Saturn's intricate system of rings. And with so much to explore, Cassini would need all the time it could get. When Cassini was launched, scientists hoped that their spacecraft would survive for 4 years. In fact, Cassini has more than doubled that. And after 8 years and counting, it's beginning to reveal details that a shorter mission would have missed. Details that will ultimately help scientists solve some of Saturn's most baffling mysteries. It's easy to understand why the extra time has been so important for Cassini. Just consider how profoundly things can change on our own planet, simply by watching the yearly cycle of the seasons. Without taking a single step, the journey from winter to summer is like a trip to a whole new world. Like Earth, Saturn is also a planet of seasons. The difference is that because Saturn is so far from the Sun and its orbit so large, a year on Saturn takes nearly 30 years on Earth. When Cassini first arrived at Saturn, the planet's southern hemisphere was in the midst of late summer. The South Pole was tilted toward the Sun, giving Cassini's cameras a superb view of the planet and its rings from below. But over the next several years, as Saturn proceeded along its orbital path, southern summer gave way to northern spring. As the seasons changed, so too did the angle of the Sun, and Cassini's cameras faithfully recorded a fascinating transformation. Month by month, the North Pole slowly emerged from darkness, while the broad shadows of Saturn's multiple rings gradually narrowed and shifted. By August of 2009, Saturn was at equinox, and for the first time in 15 years, sunlight was shining directly onto the planet's equator. At equinox, the sun illuminates the rings from the side so that their shadows on the planet below converge into a single pencil-thin line, dividing Saturn evenly in half. While across the vast ring plane, a host of rare and striking visual effects appear. Here, a narrow opening in the rings seems to be the work of a cosmic scalpel, but appearances are deceiving. What seems to be a cut in the rings is simply the shadow of Saturn's moon, Mimas, stretched out across the ring plane. Such tricks between light and dark, rings and moons, can only be observed near the time of the equinox, and they are fleeting. Here, Cassini tracks the shadow of a different moon, Tethys, sweeping over the rings in a matter of minutes. Looking more closely, the same effect allows Cassini to spot something new, a tiny moonlet just 300 meters across, embedded within the rings. Such objects are normally invisible, but during Saturn's equinox, their presence is revealed by the shadows they cast. Here, a jagged line of shadows reveals not just a single moon, but what appears to be an entire mountain range towering 2.5 kilometers above the ring plane. These peaks may be more like clouds than mountains. Puffs of dust-sized particles deflected upward by larger chunks of icy material orbiting within the thickest and brightest portion of Saturn's rings. Meanwhile, as the sun begins to warm the planet's northern hemisphere, there is more for Cassini to discover. Not just in the rings, but in the hazy depths of Saturn's atmosphere, where a dramatic change in the weather is about to unfold. For the planet Saturn, 1.5 billion kilometers from the sun, the concept of summer is a relative term. Here, at the outer reaches of the solar system, the sun is just 1% as bright as we experience it on Earth. That's far too weak a light for solar panels to be of any use. So the Cassini mission to Saturn relies on the decay of nuclear isotopes to power its cameras and electrical systems. Yet as the seasons change on Saturn, there are signs that the sun can still have a profound effect on this majestic planet. By late 2009, Cassini had been in orbit around Saturn for over 6 years. It had witnessed Saturn's spring equinox and was watching closely as summer approached for the planet's northern hemisphere. The change brought more light and more heat to the northern half of Saturn's hazy, cream-colored atmosphere. Saturn's clouds are over 100 kilometers thick. Their tops are made of frozen ammonia ice. But far below, there is a layer of water vapor. And as heat generates turbulence in these clouds, the result is lightning. In November of 2009, Cassini's cameras, for the first time, witnessed an electrical storm rattling the night side of Saturn. And just like on Earth, the bright flashes of electrical energy came with bursts of radio static. Clearly, the changing seasons had awakened something in Saturn's atmosphere. 1 year later, on December 5th, 2010, Cassini snapped this image of Saturn on the same day the spacecraft's radio and plasma experiments detected lightning in the atmosphere. Although no one realized it at the time, this image contains the first hint of a giant storm about to erupt in Saturn's atmosphere. In this first image, the storm appears as a tiny spot relative to the planet, even though it is already 2,000 kilometers across and growing fast.
Within 3 weeks, the spot had evolved into a vast and complex storm system with towering clouds of white ammonia crystals. For months, the great storm raged on, becoming one of the largest disturbances ever seen on Saturn. Over the course of 2011, Cassini's electronic eyes revealed the storm's progress in unprecedented detail, using its infrared vision to peer further into the planet's unsettled atmosphere. False color views like these helped reveal the storm's structure. Here, red indicates the deepest levels exposed by the storm's churnings. Eventually, the storm wrapped itself all the way around the planet, forming a continuous band of chaotic turbulence. For an entire year, it had given scientists their best chance ever to witness the complex workings of Saturn's atmosphere in action.
Scientists still have a lot to learn about how Saturn changes with the seasons. And those changes don't just apply to Saturn's atmosphere, but to its largest moon, Titan, one of the most intriguing destinations in the solar system.
Titan is more than a moon. It is like a planet unto itself, with a dense atmosphere made of nitrogen gas and a thick orange-colored haze layer that acts like a natural smog. Although the smog conceals Titan's surface from view, it only serves to raise scientists' excitement about what kind of world may lie underneath. Even before spacecraft were sent to Saturn, astronomers realized that conditions on Titan's surface were bound to be interesting, because temperatures and pressures there allow methane to exist as a liquid, a solid, and a gas. Could Titan have rivers and lakes of liquid methane? That is the question scientists hope to finally answer with Cassini. In October 2004, 3 months after arriving at Saturn, Cassini was scheduled to make its first close pass of Titan, and expectations were running high. The results were astonishing. Through its infrared eye, Cassini could see that the surface of Titan was far more interesting than anyone had expected, with a sharp separation between light and dark regions that strongly resembled coastlines on Earth. Meanwhile, Cassini's radar unveiled a surprisingly diverse surface that suggested a complex geologic history. But where were the lakes and rivers of methane? Cassini couldn't tell. Because there are no shadows under the foggy haze of Titan, there's no way for the infrared camera to reveal whether the light or dark areas were of different elevations. However, in close-ups, all of the areas seem to be windswept, suggesting that both the light and dark areas seen here are just different kinds of dry land. Fortunately, Cassini had one more tool to help make sense of what it was seeing on Titan. The Huygens probe, built by the European Space Agency, had come to Saturn attached to Cassini. In January of 2005, Huygens released itself from the main spacecraft and plunged into Titan's enveloping haze. There, its cameras radioed back an important discovery, an aerial view showing some dark, branching channels that had clearly once been carved out of Titan's surface by some kind of flowing liquid. Amazingly, Huygens even continued operating after it hit the surface. Its final image was a tantalizing view of an alien terrain, littered with what looked like rocks, rounded by the action of a flowing liquid. Scientists knew the rocks had to be chunks of water ice, which at the extremely cold temperatures on Titan's surface behave like solid rock. But where was the liquid that had flowed over them and carved the channels? To understand what they had found, Cassini's scientists would need a change of season. When NASA's Cassini spacecraft journeyed to Saturn, the planet's giant moon, Titan, had the largest unexplored surface in the solar system. And when Cassini's infrared camera finally peered through Titan's impenetrable clouds, scientists found a world strangely divided into territories of light and dark. The light areas were easy to explain. Like Saturn's other moons, Titan's surface is mostly made of ice. But the dark regions that ran along the giant moon's equator were a puzzle. Was this the liquid methane that scientists had expected to find flowing over Titan's frozen surface? The answer proved to be more complicated. Although these dark plains may have been flooded by liquid in the past, what Cassini found looked more like dry land. Using its radar system to bounce signals off of Titan's surface, Cassini revealed row upon row of wind-blown dunes. The dunes reveal that Titan's dark equatorial zone is more of a desert than a sea. So to look for signs of liquid on the moon's icy surface, Cassini turned its attention to Titan's poles. It was here that Cassini saw its first obvious signs of weather on Titan, in the form of thick white clouds of methane circling around the South Pole. In time, Cassini would see many more methane clouds on Titan. As the season changed and sunlight shifted northward, they began appearing over Titan's equator and the North Pole. The clouds proved that Titan was a dynamic world with a restless atmosphere. But did Titan's shifting patterns of clouds also mean rain? On Earth, rain is the way that evaporated water returns to the surface, forming rivers and lakes. On Titan, conditions should be just right for methane to behave in the same way. The first clue that this is happening was this large dark spot found near Titan's south pole. Unlike the dark regions near the equator, this one had no dunes, but sharp boundaries and a shape and size that reminded scientists of one of Earth's Great Lakes. They called it Ontario Lacus. The more Cassini peered at Ontario Lacus, the more this strange dark feature seemed like a liquid body. By taking advantage of the spacecraft's radar views from different angles, scientists were even able to construct a computer-animated flyover. There are beaches here, formed by the action of moving waves. There are inlets and bays where liquid has flooded in. And there are even river deltas where dark channels appear to flow into the lake. There seems little doubt that Cassini had at last found a body of liquid methane on Titan. Now Cassini turned its attention northward, beyond the dark dune fields near the equator, and up into regions still emerging from Titan's cold, dark northern winter. What Cassini discovered there looked very much like a landscape inundated with lakes. In radar images, they stand out like pools of black ink against a ghostly white icescape. And then something much larger. Hints of a vast and jagged coastline with jutting peninsulas and great islands. It was to be Cassini's first close-up glimpse of Titan's largest liquid feature. This is Mare Kraken, the Kraken Sea, named after a legendary sea monster. As large as the Caspian Sea on Earth, Mare Kraken spreads across so much of Titan's northern landscape that its full extent has yet to be mapped. The more data Cassini gathered, the more obvious it became that it's the northern half of Titan where fluid is most concentrated. And in case anyone needed more convincing, on December 17, 2009, Cassini spotted something that scientists had long been hoping to see. It is the glint of sunlight reflecting off the mirror-like surface of the Kraken Sea. This telltale flash is the final piece of evidence that Titan truly is a world of lakes, the only world in our solar system, apart from Earth, where liquids exist naturally on the surface.
In one sense, Titan presents us with an utterly alien landscape, where water behaves like solid rock and methane gas behaves like water. But because there's an atmosphere on Titan, with wind and rain, lakes and rivers, something about this alien landscape also reminds us of home. It's not Earth as we know it, but it shows us where our own planet fits into the larger family of possible worlds, all shaped by the same phenomena.
Scientists are now considering future missions to Titan that could include dropping a boat onto one of its lakes, or perhaps the Kraken Sea. Such a spacecraft would become the first mariner to sail beyond the seas of our own planet and reveal the unknown wonders that lie await on these distant shores. When that day comes, it will not only teach us more about Titan, but confirm what the Cassini mission has shown us over and over again. That while seasons may change on Saturn, our capacity to be enchanted by this remarkable planet and its moons endures without end. To explore even the nearest worlds of our solar system, a spacecraft must journey across hundreds of millions of kilometers of interplanetary space. But in the process of doing so, it may also reach back across billions of years of cosmic history. On Earth, tracing that history presents an enormous challenge. The ceaseless movements of water, ice, wind, and volcanic eruptions, as well as the actions of a diverse and complex array of living organisms, all combine to create a planet that is never at rest. Our world is a world of the present, a world of change. To access our past, we must leave Earth behind and find those places that time has left untouched. On September 17, 2007, a NASA spacecraft began the most ambitious journey yet back through the 4.5 billion years of our solar system's history. Its goal? To open a window into a distant era when the planets as we know them today were still just forming. Fittingly, it's called the Dawn mission. While the secrets of the solar system's early history remain elusive, the place to hunt for those secrets is not. It is the asteroid belt, a zone of flying rocks and miniature worlds that forms a vast ring of material orbiting around the sun. The asteroid belt is a place of transition between the inner solar system, where small rocky planets like Earth are found, and the outer solar system, where the planets are massive spheres of liquid gas. And it's here that scientists are seeking insights into a different transition, the one that billions of years ago led from small bits of cosmic dust and debris to the planets that populate our solar system today, including at least one such planet, our own, that is capable of supporting life.
There are hundreds of thousands of objects in the asteroid belt. Most are only a few kilometers in size, tiny flying mountains that tumble namelessly through space. But a handful of asteroids are hundreds of times larger than that and much more interesting. In fact, they are just large enough to reveal the first steps on the way to making true planets.
Dawn's mission is to explore the two most massive asteroids, Ceres and Vesta. Both were discovered more than 2 centuries ago, even before astronomers realized there was such a thing as an asteroid belt. Now they are believed to be relics from a far more distant past, when objects that were several hundred kilometers in size became the building blocks of the solar system's rocky inner planets. The asteroid belt is the place where such objects can still be found. But even here, they are rare. Most of them were broken apart by collisions with other asteroids long ago. As the largest survivors of this celestial shooting gallery, Ceres and Vesta are especially important to scientists. But until now, the best views we've had show them as little more than blurry, uneven blobs. Here, the Hubble Space Telescope has taken enough images of Vesta to show the asteroid rotating on its axis. But there is only so much that can be learned from this distance. So, with a sophisticated suite of instruments and a long list of questions, the Dawn mission set out for the asteroid belt, with Vesta as its first stop. Once free of Earth's gravity, Dawn spread its 2 enormous solar panels, giving the spacecraft the appearance of a great bird in flight. The panels are part of an innovative propulsion system that generates electricity from sunlight and uses it to drive a high-speed stream of ionized xenon. This method has proved ideal for pushing Dawn along its complicated flight path, which took it past Mars in 2009 and onward into the main asteroid belt. But this is not the first time spacecraft have explored this rocky region of the solar system. In 1991, the Galileo mission on its way to Jupiter passed near enough to the small asteroid Gaspra to return this image, the first ever asteroid close-up. 2 years later, Galileo passed a much larger asteroid named Ida and discovered that it was circled by a tiny moonlet which scientists dubbed Dactyl. In 1997, the Near-Shoemaker spacecraft saw a very different-looking kind of object when it passed near the asteroid Matilda. And finally, in 2010, Europe's Rosetta mission captured this view of Lutetia. At over 100 kilometers across, it was the largest asteroid yet to be revealed. Yet all of these views, taken by spacecraft on their way to other destinations, are tantalizingly brief. This time, scientists were planning for a very different kind of encounter, one that would allow them for the first time to orbit and survey in detail the 2 giants of the asteroid belt. By July of 2011, that encounter was set to begin. After 4 long years, Dawn was finally approaching its first stop, Vesta. As Dawn's cameras zoomed in on their target,
scientists prepared to open a new chapter in asteroid exploration. They would not be disappointed. 350 million kilometers from the Sun, the battered surface of the asteroid Vesta bears witness to the solar system's violent beginnings. This is the view from the Dawn mission, the first spacecraft to closely examine Vesta in an effort to tease out some billion-year-old secrets about the formation of the planets. Although it is one of the largest asteroids of all, Vesta is tiny compared to Earth, with a surface gravity that is only 2% what we experience on our world. Yet even such a tiny gravitational pull is enough to keep Dawn in orbit around Vesta. And soon after it arrived, in July of 2011, the spacecraft set about imaging the asteroid's entire surface end to end. Like other asteroids, Dawn has found that Vesta is riddled with craters. Each crater marks the spot where another smaller object has pounded Vesta's surface at high speed. Some craters are more recent than others, with clear, sharp edges. This group of 3 craters, imaged shortly after Dawn arrived at Vesta, is nicknamed the Snowman. Other features are more mysterious. As Dawn first approached Vesta, one of its first discoveries was a set of deep parallel troughs running roughly along the asteroid's equator. Although these troughs are not craters, Dawn scientists would eventually realize that they too are related to the large-scale collisions that have rocked Vesta in the distant past.
The fate of an asteroid is determined by its encounters with others. In the early days of the solar system, asteroids such as Vesta were built up from smaller bodies that collided and stuck together.
Many of these early clumps continue to grow and combine, forming full-sized planets like Earth. But in the location that is today known as the asteroid belt, it's thought that the strong gravitational influence of Jupiter, the solar system's largest planet, scattered the asteroids and kept them from forming something larger. Instead, many were broken apart by collisions, with fragments still occasionally raining down on Vesta right up to the present time. What makes Vesta an exception is that it has survived at its current size. Relative to most other asteroids, Vesta is a giant. And while it may look like an asteroid on the outside, there is evidence that Vesta could have a planet-sized heart. Most asteroids are thought to be the same inside and out. They have been built up bit by bit out of the dust and debris that swirled around the Sun when the solar system formed over 4.5 billion years ago. Dark and primitive, they are rich in carbon, oxygen, and other elements that are common throughout the Milky Way, the byproducts of the life cycles of the stars. Vesta is known to be very different. By analyzing the sunlight that reflects off its ash-gray surface, scientists have found it is more like basaltic rocks found on Earth. Such rocks are created in the heat of volcanic activity, created when lava cools on or near Earth's surface. There are also meteorites with a similar composition,
space rocks, thought to be pieces of Vesta, which were blasted off the asteroid and later tumbled to Earth. These precious fragments suggest that Vesta was a molten body in the distant past. But how could such a small, cold world have produced lava? The answer lies with the star. A supernova is the sudden death of a massive star and one of the most violent events in the universe. For a brief moment, a supernova can outshine all the billions of stars in a galaxy combined. As the explosion rips the star to shreds, matter that has been highly energized by the supernova flies off in all directions. Of the many kinds of atoms that are created in a supernova, one of the most important to astronomers is aluminum-26, a radioactive isotope that decays over hundreds of thousands of years. Because aluminum-26 is known to have been present as our solar system was forming, scientists now believe a high concentration of this material is what gave Vesta its original heat billions of years ago. But today, as dawn patrols Vesta's pockmarked surface, there seems to be no obvious traces of past volcanic activity. In a search for subtler clues, Dawn has paid close attention to the deepest part of Vesta's surface, near the asteroid's south pole. Even before Dawn arrived, scientists knew there was a dark feature here, which they quickly realized was the shadowed hollow of a giant impact crater. Scientists have named the crater Rhea Silvia. This computer-generated perspective, based on dawn imagery, shows what it would be like to swoop down on Rhea Silvia and fly around its outer perimeter. By adding false color, where red represents high elevation and blue the lowest areas, it's possible to see the structure of this enormous crater more clearly. Rhea Silvia is, without a doubt, the largest and most impressive feature on Vesta. Nearly 500 kilometers across and 19 kilometers deep, it has a central mound that is more than double the height of Mount Everest. And as Dawn moved in for a closer look, it was soon clear that the giant crater was just as impressive in its details. Here, jagged cliffs protrude from the wall of Rhea Silvia, revealing the bedrock that lies beneath a thick blanket of impact debris. Further down, smaller impact craters with scattered boulders gouged out of Rhea Silvia's low-lying floor offer the most revealing glimpse at a part of Vesta that was once deep below the surface. Armed with these and other unprecedented views, scientists would soon discover that Rhea Silvia was the key that would help them unlock the 4.5 billion-year-old history of Vesta. But along the way, that key would also provide an unexpected turn. By April of 2012, NASA's Dawn spacecraft had brought itself to within 200 kilometers of the asteroid Vesta, much closer than the International Space Station orbits Earth. At such close quarters, Vesta's airless surface appears peppered with small craters, many of them produced when chunks of rock that were blasted off Vesta came crashing back into the asteroid. With Dawn's help, astronomers have now confirmed that the biggest blast of all came roughly 1 billion years ago, when a smaller asteroid collided with Vesta and formed its giant crater, Rhea Silvia. Now it appears that many of Vesta's unique features are tied to this ancient impact.
But when Dawn began looking at Vesta's giant crater up close, it encountered another surprise. Rhea Silvia sits on top of another crater whose outline can still be seen. Nearly as large, but 1 billion years older, scientists have dubbed Vesta's second giant crater Venenia. So now it's clear that Vesta was twice hammered by a mighty blow. Each one raised its own set of ridges and troughs, and each one excavated tons of debris that were then scattered across much of Vesta's ancient surface. But while some of Vesta's past now lies buried by these giant impacts, there are pieces of it that can be examined up close. That's because the same two impacts that carved out Vesta's largest craters also shattered its crust and mantle, blasting enough rock into space to create an entire family of smaller asteroids. It is these pieces, known as vestoids, which have occasionally found their way to Earth as meteorites, bringing us valuable clues about the nature and history of Vesta. Now those clues can be directly compared with the data that Dawn has gathered by orbiting Vesta up close. The results make clear that Vesta is a unique fossil from the solar system's deep past. At that time, its liquid interior divided into a metallic core and a rocky mantle, with minerals that become more iron-rich the deeper you go. In this way, scientists have found that Vesta is less of an asteroid and more of a miniature planet, an early result of the same process that would eventually lead to the formation of Earth in all its geologic diversity. Dawn's one-year encounter with Vesta has given us a close-up view and a new understanding of the solar system's ultimate survivor. But our explorations of the asteroids and the asteroid belt are just beginning. In the summer of 2012, Dawn's ion engine powered up and gently pushed the spacecraft out of its orbit around Vesta, putting it on course to rendezvous with the asteroid Ceres in 2015. And while Dawn moves on, scientists are also imagining even more ambitious explorations of asteroids that are closer to home. They are eyeing the so-called near-Earth asteroids, which have drifted far from the main asteroid belt and over millions of years have wandered into our own part of the solar system. The nearest of these wandering neighbors is the asteroid Eros, an irregular chunk of flying rock nearly 35 kilometers long. This was the target of the Near-Shoemaker mission, which orbited Eros in 2000 and even managed to touch down on the asteroid's boulder-strewn surface a year later. By 2019, NASA's OSIRIS-REx mission hopes to follow a similar strategy, closing in on near-Earth asteroids and capturing up to 2 ounces of material for return to Earth. Such missions hold great value for researchers trying to piece together the detailed composition and history of these nearest asteroids, and there are good reasons for doing so. Evidence suggests that in the past, asteroids colliding with Earth played a fateful role in shaping the history of life on our planet. In the future, near-Earth asteroids may become important in a different way, as a tantalizing opportunity for those seeking to harness these objects for their mineral wealth. Such a future will mean that the asteroids, which were long overlooked in the early years of space exploration, could one day become our main reason for venturing into space, and the next frontier in humanity's epic quest to reach for the stars.
water. It is Earth's defining feature. Other planets besides our own have towering mountains and vast deserts. But only on Earth do we find this: entire oceans of water in liquid form covering much of the planet's surface. Water shapes our world. It dissolves rock, moves energy around the globe, and helps make our climate livable. But most important of all, water lets chemicals mingle, including those chemicals that are crucial for sustaining life. Quite simply, without water, life as we know it would not exist. Water is so important to life on Earth that finding it has become a key goal for scientists looking for life elsewhere in the solar system and beyond. In effect, we have become cosmic dowsers, feeling around for hints that even now, water is flowing somewhere out there. The quest for water has led us to the places that at first glance seem to resemble Earth the most. Torrid Venus and desolate Mars. But surprisingly, the strongest evidence we have that water is present in liquid form elsewhere in our solar system comes from a world that is utterly different from our own. This is Enceladus, a tiny frozen moon of Saturn located 1.5 billion kilometers from the Sun. Although it is just one of dozens of moons orbiting Saturn, scientists have long suspected that there is something special about Enceladus. For starters, it has the brightest surface in the entire solar system. And another curious detail, Enceladus travels around Saturn embedded within a faint and diffuse band of particles known as Saturn's E-ring. Astronomers have long suspected that the E-ring is related somehow to Enceladus. But how? The question would be answered in 2005, when NASA's Cassini spacecraft began the first of several close passes of Enceladus during its ongoing exploration of the Saturn system. In some areas, the surface is clearly ancient, marked by craters that have accumulated over billions of years. But toward the south pole of Enceladus, the surface features tell a very different story. Here, the landscape is dominated by a strange pattern of linear grooves. In July 2005, Cassini was swooping in for a closer look at this area when it spotted a dramatic series of 4 deep fissures. Scientists nicknamed the strange markings the tiger stripes. During the same flyby, one of Cassini's instruments detected signs of a gaseous material above the moon's south pole. The gas was mainly water vapor. These clues made it clear that something truly unique is happening on Enceladus. So when Cassini next encountered the moon in November of 2005, mission controllers commanded the robotic probe to swivel around and capture an image of Enceladus backlit by the sun. The result was this incredible image showing jets of water vapor spewing from the south polar region of Enceladus. These jets must be the sources of the E-ring that surrounds Saturn, and they are among the most exciting revelations of the entire Cassini mission. Captured in the sun's glare, the jets look like geysers of icy mist. Enceladus, once expected to be a cold and dead moon, seems to have a warm and geologically active interior, and the results can be seen literally spilling through the cracks. But where is the heat coming from? Enceladus is too far from the sun to be warmed by its rays. Yet it is also too small to be able to hold on to the internal heat it acquired when it formed billions of years ago. Instead, scientists suspect that somehow Enceladus is gaining additional heat from the gravitational pull of Saturn. But whatever is heating the moon, evidence is mounting that it's been going on for a long time. For example, Cassini has revealed that a blanket of snow made up of icy particles from the geysers is building up on the moon's surface. In some areas, the blanket is 100 meters thick, an amount that scientists estimate would take 10 million years to accumulate. If Enceladus has been active for that long, it may be because beneath its icy surface lies an entire ocean of liquid water. If this is true, then the geysers of Enceladus represent the most direct evidence yet for liquid water beyond Earth. And where there is water, there could be life. But water is a dynamic substance that brings change wherever it turns up. That's why looking for change may ultimately be the best way to find water beyond Earth. In our solar system, no other planet has intrigued, excited, and misled astronomers more than Mars. Mars is the only planet with a solid surface that can be observed easily from Earth. And for generations, its rust-colored glow has beckoned would-be explorers. First with telescopes, and then with wave after wave of robot probes. What they have discovered is a world of dry rivers and ancient lake beds. A world where water flowed freely billions of years ago, forming mineral deposits and bubbling through the soil in hot springs. And it is also a world where water still exists, in frozen form, locked as permafrost in the Martian soil. But in all this exploring, is it possible we've missed the most important discovery of all?
Mars is a remarkable world with a complex history in which water once played an important role. Today, spacecraft are orbiting around Mars and roving over its surface in an effort to piece that history together. But in the process, they are also turning up some unexpected clues that suggest there may be liquid water lurking on Mars today, and we can find it if we know where to look.
Mars has received so much attention over the years, it may seem strange that only now are scientists beginning to spot these clues. But that is because for many decades, the exploration of Mars was a fleeting affair, with visiting spacecraft only surviving for a limited period of time. That changed starting in September of 1997, when Mars Global Surveyor arrived. It was the first of a new generation of orbiters that have had Mars under continuous surveillance ever since. And that is precisely what is needed to look for small-scale changes that could be a sign of water flowing near the Martian surface. At face value, such an idea seems misguided. After all, Mars is a freeze-dried world with an atmospheric pressure so low it's nearly a vacuum. Under such conditions, any liquid water on the surface would rapidly vaporize. But in June of 2000, scientists operating the camera on board Mars Global Surveyor reported an exciting find. In some of the tens of thousands of images, they found small gullies carved into the sides of canyons and crater walls. The gullies looked suspiciously like they were formed by water that seeped from the rock and flowed downhill before evaporating. And unlike those features formed where water flowed on Mars billions of years ago, the gullies looked recent, as if they were just formed. When they were first discovered, some scientists speculated that the gullies might be a sign that there are hidden reservoirs of underground water on Mars that occasionally spill onto the surface. It's a tantalizing possibility, one that became even more exciting when some of the gullies appeared to be changing from one year to the next. Perhaps water was responsible. But there was a catch. The gullies were typically found far from the equator, in craters or canyon walls that faced away from the sun. These cold and shaded places should be the least likely to yield liquid water. And that suggested another way to explain the gullies. Mars is so cold that during the winter months, the carbon dioxide in its thin atmosphere can settle onto the surface as frost. Such a buildup of CO2 could trigger landslides simply by adding weight or by pushing up on rock and dust when it evaporates. But there remain cases that are difficult to explain. In 2011, scientists working with the Mars Reconnaissance Orbiter, a spacecraft with the most powerful camera sent to Mars yet, reported that the orbiter had spotted a curious phenomenon in Newton Crater in the southern hemisphere of Mars. Images taken several months apart showed dark streaks rolling down the crater walls and fanning out along the flatter ground below. More streaks appear as the southern spring turns to summer. Then they disappear again at winter's approach. It's tempting to think that water is the cause, darkening the soil as it runs downhill, like a wave creeping across dry sand. But the discolorations last for months, too long for liquid water to linger near the surface of Mars. Instead, water from melting ground ice may cause a chemical or physical change in the soil as it flows just below the surface. If scientists were to verify that liquid water can sometimes occur on Mars, even briefly, the implications are enormous, because that water might be all that's needed to sustain hidden colonies of Martian microbes. It's an incredible idea, one that could put an alien form of life within our grasp. But even as we imagine building more sophisticated machines that will further the quest for water on Mars, another kind of spacecraft has transformed the search for water in the universe by taking it to the stars. If there is one idea about the universe that is fundamental to all others, it's that no one place in the cosmos is truly unique. In every direction in space, there are atoms, stars, and galaxies. Just as there are here, and they obey the same laws of nature. This is an extremely profound thought, because it means that if life is possible here, we should also expect to find life elsewhere, wherever conditions are right. Conditions that include liquid water. Fortunately, space travel has given us a new set of tools for exploring beyond the solar system. They are orbiting telescopes that are making it possible to find planets around other stars. And they can even tell us if some of those planets show signs of having water. One such planet, designated HD 209458b, has been found circling a star similar to our Sun. Located 150 light-years away in the constellation Pegasus, it is the first planet outside our solar system to be observed crossing directly in front of the star that it orbits. Even though the planet is too faint to be seen directly, each time it does this, astronomers can measure how much the star's light dims and for how long. This has allowed them to calculate the planet's size and its distance from the star. But it can also reveal much more. As some of the star's light passes through the planet's atmosphere, it can be used to read the chemical signatures of the gases that are present there. Space telescopes have detected the signs of an extensive atmosphere around the planet, and they paint a portrait of a world that is unlike any in our own solar system. Heated by the relentless glare of a stellar inferno, the atmosphere of the planet has expanded, forming a long tail of gas escaping into space. Closer in, the atmosphere is subject to 1,000-degree temperatures and violent winds. At such extreme conditions, and lacking a solid surface, this planet is not expected to harbor life. But in analyzing its atmosphere, astronomers in 2007 made an important discovery. For the first time, they reported evidence for water vapor on a planet orbiting another star. This is exciting, if not a complete surprise. After all, water is one of the most common molecules in the universe. But seeing its signature in the atmosphere of so alien a world means that, in principle, water may also be detected on other planets that are far more similar to our own. The job of finding those planets falls to a highly specialized space telescope. This is Kepler. It is the first telescope with a reasonable chance of detecting another Earth. Kepler does this by staring continuously at a single patch of our Milky Way galaxy. By doing so, it can monitor over 100,000 stars at the same time. Every so often, one of those stars will dim for a few hours and then return to normal. If the dimming repeats at regular intervals, then astronomers know that Kepler has found a planet. One of Kepler's most exciting discoveries to date is a planet around a sun-like star simply called Kepler 22b. Kepler 22b orbits at about the same distance Earth orbits the Sun. Just the right distance for liquid water to exist, and possibly life. But Kepler 22b is also not like Earth. Instead, it is nearly 2.5 times the size of our planet. Astronomers call such a world a super-Earth. Kepler 22b could be made entirely of rock, or it could be a planet-wide ocean, a water world. Another example is Gliese 1214b, a world that circles a small red star only 40 light-years from our solar system. This planet is similar in size to Kepler 22b, but much closer to its star. This makes it easier to measure the planet's mass because of the gravitational pull it exerts on the star as it orbits. From observations of the star, astronomers can tell that the planet is not nearly massive enough to be made entirely of rock. Therefore, it is either a small rocky world with a vast atmosphere or a true water world. If this is confirmed, then the notion of a planet made almost entirely of water will no longer be science fiction. It will instead be one of our nearest neighbors.
When we search for water in our solar system and beyond, what we have found is the universe's remarkable capacity to surprise us. Instead of places that resemble Earth, we've discovered Martian gullies, geyser-spraying moons, and possibly ocean planets.
What all of these findings point to is the incredible variety of environments in which liquid water can exist across the cosmos. On Earth, almost everywhere we find liquid water, we find life. If our world is any indication of conditions elsewhere, then ours is a universe teeming with life.